This is another example of how we can use the buoyant force to solve a problem. The problem statement is as follows. The ancient Greek engineer Archimedes was tasked with finding if a crown was made of gold or not. And he decided to find out by dunking it. Imagine that before he dunked it, the crown was measured to have a mass of 0.917 kilograms in modern units. In the water, the crown appears to have a mass of 0.841 kilograms. And we were asked first, what is the buoyant force felt by the crown? Second, what is the volume of the crown? And then finally, is the crown made of gold? Any problem involving buoyant force is a force problem, a Newton's second law problem. And so we should treat it like any other Newton's second law problem. Step one in the problem-solving process is to draw a diagram showing all the forces acting on the object. In this case, we want to draw a diagram showing all the forces acting on the crown as it hangs from a scale in the water. We have first the tension force upward from the string. Second, we have the weight force downward, which is the true mass times g. And then finally, we have the buoyant force from the water upward. These are the three forces which are acting on the crown. Now, it is worth noting at this point that the force measured by the scale is the tension force. The scale does not measure the weight force. No scale can measure the weight force. A scale is always measuring some other force and claiming that it's equal to the weight force. And if the buoyant force did not exist, then if we were not in water, in other words, then certainly the tension force would be equal to the weight force. The crown is hanging there motionless, so these two forces must be in equilibrium. So the tension would equal the weight force and the scale would tell us the true mass. But because we have a buoyant force acting on the crown as well, you don't have this two-force equilibrium. Tension is what the scale measures. All the scale can do is tell you how hard it has to pull up. And in this case, that is not going to be equal to the weight of the crown. That tension force is, in fact, going to be a false weight, a deceptive weight, a false mass multiplied by g. Out of the water, it's the true mass times g. But in the water, we get a false reading, a false mass times g. And the problem tells us that that true mass is 0.917 kilograms, and the false mass is 0.841 kilograms. Step two is to select a coordinate system. That's a rather easy task since we only have forces in the vertical direction. So let us call upward positive, just purely arbitrarily. That means we can skip step three because all the forces involved are in the vertical direction, and so we do not need to break any forces up into components. So we can go directly to step four, use Newton's second law to find out what you need to find out. Right, we are asked first to find the buoyant force felt by the crown. We realize that since the crown is hanging motionless in the water, the acceleration in the y direction for the crown is going to equal 0. So when we turn to Newton's second law, sum of the forces in the y direction equals mass times acceleration in the y direction. We realize it must be 0. In other words, the three forces are in equilibrium. Those three forces are the tension force upward, the true weight downward, and the buoyant force upward. All those three forces must be in equilibrium. Solving this equation for the buoyant force, we get that the buoyant force is the true mass times g, the true weight, minus the tension force, which, remember, that tension force can be thought of as a false weight. So it is the false mass times g. Looking at this another way, we realize that the only reason that there's a difference, the minus sign, between the true mass and the false mass. The only reason there's a difference between the weight out of water and the weight in water, the only reason there's a difference between those two numbers is because there's a buoyant force involved. If there were no buoyant force, these two numbers would be the same. So now we can plug in the values for the true mass, 0.917 kilograms, and the false mass, 0.841 kilograms. Always remember that we need to multiply by g because these are forces. These are weights, not masses. So we must always multiply by 9.8. That gives us a buoyant force of 0.7448 newtons. Since we have three significant figures in our data, we would report this as a buoyant force of 0.745 newtons. The next question asks us, what is the volume of the crown? It is important to note that we cannot use the density formula for this. We cannot find the volume from the density because we are not sure that the crown is made of gold. So we must take a different approach. Now we do have a formula for the buoyant force that says the buoyant force is equal to the density of the fluid times g times the volume submerged. All right, now in this case, the crown is completely submerged. So the crown is submerged. So we can say that the buoyant force is equal to the density of water, we're not in seawater, we're just in pure water here, times g times the volume of the crown. Solving this equation for the volume of the crown, we get that the volume of the crown is the buoyant force divided by the density of water times the acceleration due to gravity. Right, so that's going to be 0.7448 divided by 1,000, the density of pure water, times 9.80. That gives us a volume for the crown of 7.6 times 10 to the minus 5 cubic meters. Now that's a very, very small volume, but you must remember that a cubic meter is really big. A cubic meter is a huge amount of volume, so it's not surprising that a thin strip of metal that one wears upon one's head would have this kind of small volume. Once we have the volume in hand, we can address the issue of whether or not the crown is made of gold by determining the density of the crown. Now, the density of the crown is going to be the true mass. We do not use the false mass here. We use the true mass, the mass out of water, divided by the volume of the crown. Now, that's going to be the true mass, 0.917 kilograms, divided by the volume of the crown, 7.6 times 10 to the minus 5 cubic meters. That gives us a density of 12,065 kilograms per cubic meter. This is a density far less than the density of gold. The density of gold is 19,300 kilograms per cubic meter. So this crown is not pure gold. It is very likely gold mixed with some other substance.